Okay, so we continue our quest to find general solutions of higher order linear differential equations. Now, the method of undetermined coefficients is wonderful, and those are that, first of all, it only applies to differential equations with the right-hand side of the form from that table in your textbook, meaning basically sums and multiples of exponentials, polynomials, or sine and cosine. So it doesn't apply at all if you have something else, like a logarithm on the right-hand side, or tangent, or secant, or, well, other stuff. The other restriction is that the left-hand side must have constant coefficients. Now, in this section, we're going to see a technique that, in theory, has none of those restrictions. So let's consider a linear second-order differential equation. All right, so other than the fact that this is linear, there's really no restrictions imposed on it. These coefficients can actually be non-constant. They can involve x. And of course, the right-hand side is not necessarily 0, so this doesn't have to be homogeneous. Okay, so let's play around with this. The first thing we're going to do is we're going to write it in standard form. Of course, that means that the leading coefficient is 1, so we're just going to divide everything, or assume that we've divided everything by a2 of x. So we're going to get y double prime plus, and we'll just call the new coefficient of y prime p of x, and the new coefficient of y we'll just call q of x, and the new right-hand side we'll just call f of x. Okay, now let's assume we have a complementary solution. As this is a second-order differential equation, we would expect our complementary solution to have two parameters. So we have c1, y1, and c2, y2, with y1 and y2 linearly independent. And recall, the complementary solution is the solution to the associated homogeneous equation. So that would be if f of x were equal to 0, solve that differential equation, and let's assume we've done that, and we have our yc right here. And of course, we have no trouble doing this as long as at least p and q are constant, but the method we're going to see here doesn't even require that. So we now seek a particular solution yp. Now we know that we cannot just assign yp to be a constant multiple of y1 and another constant multiple of y2, because then yp itself would not be independent of the complementary solution. So what we're going to do is say, well, let's write it this way anyway, but instead of using constant coefficients, we'll put variable coefficients. So what we're going to do is we're going to let the particular solution yp be some function of x, we'll call it u1, times the first solution, plus some function of x, call it u2, times the second solution. So these used to be the parameters c1 and c2, but now we're replacing them with variables. And this is, of course, where the term variation of parameters comes from. So our job is to really figure out what the heck u1 and u2 are in terms of y1 and y2. And if we can figure that out, then boom, we have our particular solution. So let's note something. Yp, of course, is u1, y1 plus u2, y2. And let's just remember those are functions, so I don't want to write of x next to each one for notational convenience. The first derivative of this thing is going to require the product rule on both terms. So we have u1 prime y1 plus u1 y1 prime plus u2 prime y2 plus u2 y2 prime. All right, and taking a second derivative, this is going to give us 8 terms because each of these terms needs the product rule. So we're going to have u1 double prime y1 plus u1 prime y1 prime plus u1 prime y1 prime plus u1 y1 double prime plus u2 double prime y2 plus u2 prime y2 prime plus u2 prime y2 prime plus u2 y2 double prime. Ugh. Okay, we have a couple of like terms that we can combine, but let's defer that till a little later. Now, what we're going to do is we're going to substitute yp double prime, yp prime, and yp into the original differential equation. So the original differential equation, well, after it was in standard form, was y double prime plus py prime plus qy equals f of x. All right, so let's put all these pieces in and see what happens. It's going to be a bit of a mess at first. So yp double prime is this big thing right here, and we can just write it down, but let's combine the like terms while we're at it. So we have okay, and then we're going to add to that p multiplied by yp prime, which is this thing. And we're adding to that q multiplied by yp, which is not too bad. And all of that monster is equal to f of x. All right, so let's see what we're working with here. Well, let's notice that we have only 3 terms that have a u1 without any primes. So let's factor the u1 out of those 3 terms. So we have u1 times y1 double prime plus py1 prime plus qy1. We also have only 3 terms that have simply u2, not u2 prime or double prime. So we can factor u2 out of those guys. All right, so let's underline the terms that we've already handled. So what are we left with? Well, we have p times u1 prime y1 plus u2 prime y2. And then we have 4 more terms that we haven't dealt with yet. So that's okay, and of course this is still all equal to f of x. The first bit of magic is going to happen right now. Remember, y1 and y2 are fundamental solutions to the associated homogeneous linear differential equation, which means that when we substitute y1 into the original differential equation, well, that's a solution to the homogeneous version, so that means that the right-hand side will give you 0. So that means that this entire expression here is equal to 0, and this entire expression here is equal to 0. Okay, well, what are we dealing with now? So we have p times u1 prime y1 plus u2 prime y2. And, well, what have we got here? So we've got a u1 double prime y1, and we have 2 copies of u1 prime y1 prime. So actually, this is the derivative of u1 prime y1 with a leftover u1 prime y1 prime. And we also have the derivative of u2 prime y2 with a leftover u2 prime y2 prime. And of course, this is all equal to f of x. So we have p times u1 prime y1 plus u2 prime y2 plus the derivative of this thing plus u1 prime, y1 prime, plus u2 prime, y2 prime, and that's all equal to f of x. And again, let's not forget what we're after. We want u1 and u2 in terms of y1 and y2. Because once we know that, we can go back and have our particular solution. Now, in truth, based on the way we defined u1 and u2, there really isn't enough restriction to truly determine what they are, because many different functions would satisfy this condition. So this actually gives us room to impose a further assumption that will preserve the integrity of what we've done so far. And that is to assume the following. Let's assume further that the first derivative of u1 when multiplied by y1 plus the first derivative of u2 when multiplied by y2 is equal to 0. And why would we do that? Because that reduces our entire equation to simply this part right here. Okay, so we have a system of equations. We have y1 times u1 prime plus y2 times u2 prime is equal to 0. We have y1 prime times u1 prime plus y2 prime times u2 prime is equal to f of x. So this is just a system of two equations with two unknowns. Currently, the unknowns are u1 prime and u2 prime, and they just have coefficients of y1 and y2 and y1 prime and y2 prime. Now, you can solve this equation on your own if you like, using any technique that you know to solve a system of linear equations, and you would get u1 prime as some expression involving y1 and y2, and you get u2 prime equal to some expression involving y1 and y2. Now, what I'm going to do to solve this is use a matrix, because it's probably the most straightforward way to approach this particular system. So if you don't remember how to use a matrix to solve a system of equations, that's okay. It's not required for this section, but it is the most straightforward way of solving this, in my opinion. So we have this first matrix times that second matrix equals this third matrix. And this product would be obtained through matrix multiplication. For instance, this one equation here is the dot product of this row with this column, and this equation is the dot product of this row with this column. And it's not at all a coincidence. The determinant of this matrix is the Wronskian. Okay, so we're after u1 and u2. So we'll just isolate this column by multiplying the matrix on the right-hand side by the inverse of the coefficient matrix here. And to find the inverse of a 2 by 2 matrix is really straightforward. You just divide by the determinant of the matrix, which of course is the Wronskian in this case. You swap the order of the diagonal entries, and you negate the entries along the anti-diagonal. And we're going to multiply that matrix by okay, well, let's actually do the product on the right by taking the dot product of the top row with the column. So we're going to get negative y2 times f of x. And the other entry is going to be the dot product of the bottom row with the right column. So we get positive y1 times f of x. And equating the entries, we get u1 prime is equal to negative y2 times f of x divided by the Wronskian. And we get u2 prime is equal to y1 times f of x divided by the Wronskian. Again, if you're rusty on your matrices, you don't necessarily need to follow everything that just happened, because we've got the result that we need now. You can obtain this result just by solving the system one of the classic algebraic ways. But once you take linear algebra and you've worked with matrices, you're going to realize that one of the great things about matrices is that they're placeholders for the most common behaviors in algebra. And that's why solving this particular system with a matrix is probably the most straightforward way to go, because you don't have to reinvent the wheel. Also, it involves the Wronskian, and we already have a name for that. Now, remember, what are we after? U1 and U2. So merely integrating U1 prime and U2 prime will yield suitable choices for U1 and U2. That will allow us to define the particular solution as U1 y1 plus U2 y2 as desired. And of course, the general solution will simply be the sum of the complementary solution plus the particular solution that we just found. Remember, the complementary solution is C1y1 plus C2y2, and the particular solution is U1y1 plus U2y2. All right, so yeah, that was a very involved motivation for this process. This would be a good example of a situation where in practice we don't really want to go through that entire process. So we're going to just start from these particular equations right here to generate our U1 and our U2 and go from there. All right, so let's use the method of variation of parameters to solve this particular differential equation. And you may recall that we actually already did solve this one in section 4.4 using the method of undetermined coefficients. And that's because 3e to the x is formatted in such a way that we can do that. And this was our solution. So this makes it a perfect test to see if variation of parameters will get us to the same place. So let's recall a complementary solution. That was yc is equal to c1 e to the x plus c2 e to the negative x. And again, the complementary solution is easily determined by considering the associated homogeneous differential equation, and of course, solving its auxiliary equation as a quadratic. So in this particular case, we can see that our y1 will be e to the x and our y2 will be e to the negative x, because we're going to need those to calculate our u1 and u2. So we're also going to need the Wronskian. That's the determinant of y1 and y2, y1 prime, y2 prime. So in this case, so for a 2x2 matrix like this, the determinant is very straightforward. It's the product along the diagonal here. So that would be e to the x times negative e to the negative x, and subtracting the product along the anti-diagonal. So this is -1 minus 1, which is -2. All right, so now we're going to let u1 prime be negative y2 f of x divided by the Wronskian. So that would be negative y2, which is e to the negative x, times f of x, which is 3e to the x, divided by the Wronskian, which is -2. So here we get 3/2. u2 prime is y1 f of x divided by the Wronskian. So y1 is e to the x, f of x is 3e to the x, and the Wronskian is -2. So our u2 prime is -3/2 e to the 2x. All right, so to find u1 and u2, we just need to integrate u1 prime and u2 prime. Again, we have the freedom to select any constant that we want in this situation, so let's just choose the constant equal to 0. So we're letting u1 be 3/2 x. And u2 is the antiderivative of u2 prime. This one won't be quite as straightforward, but it's pretty straightforward. So we're going to get negative 3/4 e to the 2x. Again, plus c, but let's just assign the c to be 0. So let's write down our particular solution. Yp, of course, being u1 y1 plus u2 y2. So that's going to be 3/2 x y1, which was e to the x, minus 3/4 e to the 2x, and then y2, which was e to the negative x. So here's our particular solution. And that means that we can put together our general solution. The general solution being y equal y complement plus y particular. And y complement was c1 e to the x plus c2 e to the negative x. And now we'll add our particular solution. All right, and we would be done, except for one thing. This last term of our particular solution turns out to be redundant because we already accounted for constant times e to the x. So we can actually just throw it away. So our general solution is just this guy. And if you compare it to the general solution that we obtained using the method of undetermined coefficients, you'll find that we got the same answer, of course, because math is math. It always wins. All right, here's an example for which the method of undetermined coefficients would not even apply because the right-hand side is tangent. So that's not, e to the x or a polynomial or sine or cosine, or sums and multiples of those things. Okay, so of course the first thing we'll do is we'll find the complementary solution. But we've done this one several times. This is c1 cosine of x plus c2 sine of x. So we can see that our y1 will be cosine of x, and our y2 will be sine of x. All right, so next thing we should do is calculate the Wronskian. So that's cosine and sine, and then derivative of cosine and derivative of sine. So we're going to see that this determinant is cosine times cosine minus negative sine times sine. All right, well, using a really obscure, barely known trigonometric identity, that evaluates to 1. So our Wronskian is 1. Well, that's great. So, all right. So u1 prime is negative y2 times f of x divided by that Wronskian, which is of course just 1, so that's nice. So this will be negative y2, that's sine of x, times f of x, which is tangent of x, and that's all divided by 1. So negative sine of x times tangent of x. All right. u2 prime is positive y1 times f of x divided by the Wronskian. So y1 is cosine of x times f of x, which is tangent of x, divided by 1. This one actually reduces to sine of x. And so now we just have to integrate both of those to establish what u1 and u2 are. Okay, so integrating sine times tangent, let's write that in terms of sines and cosines. Perhaps if we used the Pythagorean identity here, we would see 1 minus cosine squared. Let's see what this does. That's going to do it. So we're going to get cosine of x minus secant of x. So we get sine of x minus antiderivative of secant. and we don't bother with the constant here. All right, so that'll be what we let u1 equal. u2 is, of course, found similarly. u2 prime was sine of x, so this will be considerably more straightforward. So u2 will be negative cosine of x. All right, so our particular solution is u1 times y1 plus u2 times y2. So u1 times y1 is u1. We have sine of x minus all of this loveliness. And that's multiplied by y1, which is cosine of x. And we'll add u2. I guess we'll just subtract negative cosine of x times y2, which is sine of x. Okay, so before we pair this off with our complementary solution, we get a little bit of cancellation, because if this cosine distributes, we get cosine times sine minus cosine times sine. Okay, so we're left with negative cosine of x times ln of secant of x plus tangent of x for our particular solution. So all we have to do is add that to the complementary solution, and we have the general solution. So the complementary was c1 cosine of x plus c2 sine of x. And now we're going to add this thing. I guess we'll subtract it. Cosine of x times ln of secant plus tangent. And there we are. General solution. All right, so for this one, again, we have to find the general solution of this non-homogeneous second order linear differential equation. So step 1, solve the associated homogeneous equation. All right, so this time we'll do the steps. Get that auxiliary equation, which factors quite nicely. And that tells us that we have m equals 1 with multiplicity 2. So m equals 1 and m equals 1. And therefore, our complementary solution is going to be c1 e to the m times t, so that's just t, plus c2, and then t e to the t, because it's repeating the form. So here we can see, let's call this guy y1. y1 will be e to the t, and y2 will be t e to the t. Okay, so the next thing we need is to find the Wronskian, because we know that's part of how we find u1 and u2 prime. Derivative of t e to the t needs the product rule because it's dumb. So this product will be e to the t times e to the t plus t e to the t minus this product here, t e to the t times e to the t. So this is e to the 2t plus t e to the 2t minus t e to the 2t. So we just get e to the 2t. All right, so u1 prime is negative y2 times f of x divided by w. So negative y2 is negative t e to the t, and f of x was the right-hand side of that differential equation. So e to the t arctangent of t, all divided by the Wronskian, which is e to the 2t. So u1 prime is negative t times arctan of t. And we are going to have to integrate that, but we'll worry about that in a minute. Let's get u2 prime, which is positive y1 f of x divided by w. So positive y1 is just e to the t, And then f of x is e to the t arctan t, and this is all divided by e to the 2t. That's nice. So our u2 prime is simply arctan of t. So now we'll determine u1 and u2. So u1 is the antiderivative of u1 prime. And u1 prime was negative t times arctangent of t. So, okay, well, this is going to require integration by parts. Let's let u be negative arctangent of t. So this is u times v, that's negative 1/2 t squared arctan of t. And then minus, which will be a plus, 1/2 times the integral of t squared over 1 plus t squared. Okay, so this integral you can do with long division, but why don't we do the little move where we just add 1 and subtract 1, so we get 1 minus 1 over 1 plus t squared. That's much better. So we can integrate both parts of that. We're going to get 1/2 t and then minus 1/2 arctan of t. And again, we can assign a constant of 0 to u1. So that big mess there is our u1. Okay, so now let's find u2. So u2 is antiderivative of u2 prime. And u2 prime was arctan of t dt. So this one also will require parts, but it'll be a little bit easier than the last one. So uv, that would be t times arctan of t minus v du. So that's t over 1 plus t squared dt. And integrating this thing, you can let u be 1 plus t squared. So your du is going to be 2t dt, which means this is going to be 1/2 of du over u. So that's just going to give this form when we're done. All right, so we've got our u2. Lovely. So where are we here? Well, let's build our particular solution. So that's yp is u1 y1 plus u2 y2. So u1 was negative 1/2 t squared arctan of t plus t over 2 minus 1/2 arctan of t. And that's all being multiplied by y1, which is e to the t. And we're adding to that u2, t arctan t minus 1/2 ln of 1 plus t squared, and multiplied by y2, which was t e to the t. Okay, so this is our particular solution. And now we can finally write down the general solution. It's complementary solution plus particular solution. So the complementary was c1 e to the x, those were t's, c1 e to the t plus c2 t e to the t plus all of that loveliness. So we'll just distribute the e to the t. So we're going to have minus 1/2 t squared e to the t arctan of t. And notice that if we distribute e to the t over 2, we're going to get a redundant term to the t e to the t term. So let's skip that one, but we'll keep going. Then we'll get minus 1/2 times e to the t times arctan of t, then plus t squared e to the t arctan of t. Oh, wow, that's the same term as this one up here. So why don't we just combine those right now? And that means negative 1/2 of this thing plus 1 of this thing will be positive 1/2 of that thing. Excellent. So last thing is just to distribute the t e to the t into this guy. Okay, so this huge thing is indeed our general solution. And as ugly and complex as it is, notice it still just has the 2 parameters because this was a second order differential equation.